we will be looking at the potential energy of a dipole in an external field. That is, what is the total amount of potential energy which is stored in an electric dipole when it is placed in an external electric field. So to do this, firstly we will take the uniform electric field, that is uniform external electric field due to an unknown source, and we will be taking a electric dipole AB with negative charge at A and positive charge at B, and we will find out that the positive charge will experience a force due to the external field in the direction of the field, whereas the negative charge will be experiencing a force opposite to the direction of field, and hence due to this there is a rotation which is created in the dipole. That is, the dipole is rotated, and now initially the dipole is inclined at an angle theta. Now when the initial inclination of angle is theta and the dipole is placed in this particular angle of inclination, the dipole is now going to get rotated in this way. So due to this there will be a torque which is produced, that is, the torque experienced by this dipole will make the dipole to rotate along the clockwise direction. So now during this clockwise direction rotation, the torque experienced by the dipole due to the external electric field is given as torque tau bar equals to P bar cross E bar. This derivation has already been done in the chapter of electric charges and fields. You can just go through with it. And now the work done by this particular torque in rotating the dipole by a small angular displacement theta can be given as dW equals to tau d theta. Now since the torque and the angular displacement d theta both are in opposite direction, so we get P minus P into E sin theta d theta. Now remember one thing, this is nothing but P into E sin theta, right? Yeah. So we have this, that is, in the vector notation the cross product is given as P into E sin theta n cap for P bar cross E bar. The same thing I have substituted for tau here, but since tau and d theta, that is the rotation of the dipole is in the direction opposite to that of the applied torque, we get negative sign here. So negative minus P into E sin theta d theta, so obviously the work done is negative, and then the total amount of potential energy which is stored during this rotation, that is, if I am going to rotate this particular dipole against the field, that is against the direction of field, if I want to move it, then the potential energy, that is the work which is done, will be negative, right? So if I am going to actually rotate this in the direction of the field, that is, if I am going to rotate it in such a way that the potential energy stored is positive, that is, I am going to go along the field of the, along the direction of the field. I am not going to do the work which is against the direction of field. In such a case, the potential energy stored will be du is equal to minus dW equals to plus P into E sin theta d theta. Now remember one thing, initially while finding the work done, this work is done in rotating this dipole against the direction of the torque, right? So if I am going to go with the direction of the torque, then I will get this as plus P into E sin theta d theta. So I am going to go both the ways, that is, I am going to find out, to define the potential energy, obviously I need the work to be done against the direction of the field, right? So against the direction of the field means I am going to try to move this positive charge against the direction of field, and I am going to do some work in moving this minus q charge in the direction of the field. That is, always remember the work is done against the electric field, against the direction of electric field. So that is what I have done here, that is against the direction of the torque I have done the work, and then the potential energy is nothing but minus dW, because now I want to find out what is the change in potential energy. So change in potential energy is minus dW equals to P into E sin theta d theta. Now to find out what is the total potential energy which is stored in this dipole, when it is, I am going to take the two extreme conditions here, that is, one extreme condition is with respect to the normal, that is with respect to the 90 degree, that is pi by 2 radian. If I am going to take the angle of inclination theta to be pi by 2 radian initially, that is if I am going to align it perpendicular to the direction of the electric field, then from perpendicular position to a position where theta is equal to theta, if I want to find out the change in potential, then the total change in potential will be given by integral of bu between the limits pi by 2 to theta equals to p into e integral of sin theta d theta between the limits pi by 2 to theta. On integrating, we get u theta minus u of pi by 2 equals to p into e into sin theta, integration is minus cos theta between the limits pi by 2 and theta. Now remember one thing, here I have to substitute the upper limit first and the lower limit next. So the same thing we are doing here, u of theta minus u of pi by 2 equals to minus p into e cos theta, minus of minus is plus, cos pi by 2 is obviously equal to 0, right? So I am not going to write that part. So instead I will write only the upper limit has been substituted. So I get the change in potential in rotating the dipole from pi by 2 radian to theta can be given as minus p into e cos theta, or it can also be given as the dot product, that is minus p bar dot e bar. Now, as I already discussed in the last video, when we spoke about the system of potential energy stored in a system of two charges, I had already told you that the potential, electric potential and electric potential energy have been allowed a certain amount of freedom in choosing their origin. So when we talk about the origin, it is not only with respect to the Cartesian coordinate system, it can also be with regards to the polar coordinate system. That is, we can also talk in terms of the angles. So here in this case, the initial position, that is the initial angle of inclination, can be taken as the origin vector, that is theta is equal to pi by 2, I can take it as origin, and at that particular position u of pi by 2 can be taken as equal to 0. That is, at angle of inclination of pi by 2 radian, the potential energy stored in the dipole can be assumed to be equal to 0. So when I talk about this, when I substitute this u of pi by 2 equals to 0, then I get the total potential energy stored when the dipole is rotated to an inclination angle of theta as equal to minus p bar dot e bar. So this is about your electric potential energy which is stored in an electric dipole when it is placed in an external electric field. Thank you.